Welcome to this lecture on experimentation, a fundamental topic in research methodology. As students of zoology, you will often need to understand not just what happens in the natural world, but why it happens. Experimentation is the ultimate scientific tool that allows us to answer those why questions with absolute confidence. Let us dive in and explore how it works. To begin our journey, let us imagine a simple, everyday scenario. Imagine you are baking a cake, and you want to know if adding an extra egg makes it fluffier. To find out, you bake two identical cakes side by side. You keep the flour, sugar, and baking time exactly the same, but you add one extra egg to the second cake. When they come out of the oven, any difference in fluffiness can be confidently attributed to that extra egg. This simple act of changing just one specific thing while keeping everything else exactly the same is the very heart of experimentation. Now that we understand the basic idea through our cake analogy, let us formalize these concepts using scientific terminology. In any experiment, we have specific names for the factors we are looking at. The independent variable is the specific treatment or cause that the researcher actively manipulates, like the extra egg. The dependent variable is the final outcome or effect we are trying to measure, like the fluffiness of the cake. Finally, we have extraneous variables. These are all the other outside factors that could potentially influence the outcome, such as the oven temperature or the exact amount of sugar used. Building on those definitions, we must highlight the most critical step in this process, which is control. While manipulating the independent variable, the researcher must strictly control all extraneous variables. Why is this so important? Because if the oven temperature fluctuated while baking our second cake, we would not know if the extra egg or the heat caused the change in fluffiness. By isolating the specific variable of interest, the researcher can confidently attribute any observed changes directly to their intervention. This rigorous control and manipulation are exactly what separate a true experiment from mere observation, where a researcher simply watches what happens naturally. Understanding this strict control leads us to why experimentation is so highly valued. Experimentation is considered the absolute gold standard in scientific research because it is the only method that can definitively prove causality. Causality means that one specific thing directly causes another. Without experiments, we would only have correlations, which merely tell us that two things are related, but not if one actually causes the other. In the real world, this distinction is vital. For example, pharmaceutical companies use highly controlled clinical trials to prove that a new life-saving drug actually cures a disease, rather than just happening to be taken by people who recover naturally. Having established the conceptual foundation, let us look at how we can represent an experiment mathematically. To truly understand how an experiment works, we use a simple functional equation that acts as a blueprint. The equation is y equals f of x plus epsilon. Here, the symbol y represents the dependent variable, which is the final outcome we are measuring. The symbol x represents the independent variable, the specific treatment we manipulate. The function f of x represents the true underlying relationship or effect that x has on y. Finally, the symbol epsilon represents the error term. The real world is messy, and epsilon accounts for all the extraneous variables and random variations we can't perfectly control. If we increase the strength of our treatment x, we expect a corresponding change in y, assuming epsilon is kept small. Now that we have our mathematical blueprint, let us see this with a concrete example. A university professor wants to know if a new interactive teaching method improves student test scores compared to traditional lectures. The professor randomly assigns 60 students into two groups of 30 to ensure the error term, like natural intelligence, is evenly distributed. We use our model where y sub s is the final test score, and m is the teaching method. After a semester, the experimental group scores an average of 88%, while the control group scores 75%. Because all other factors were kept identical, the professor can confidently conclude that the interactive teaching method directly caused the 13% increase in student test scores. That previous example showed a simple comparison between two distinct groups, but this brings us to an important question. What if our independent variable is not just a category, but a continuous amount? In many scientific and economic scenarios, researchers need to measure continuous relationships to find an exact rate of change. They need to know exactly how much the outcome changes for every single additional unit of the treatment applied. To do this, we adapt our basic experimental model into a linear regression equation. This allows researchers to move beyond simple comparisons and provide precise, mathematically proven formulas to optimize real-world processes. Following up on that idea, let us look at the specific formula used for these continuous relationships. We expand our basic model into a linear regression equation. Y sub y equals beta 0 plus beta 1 times x sub f plus epsilon. In this specific model, y sub y is the total outcome measured. The variable x sub f is the exact amount of treatment applied. The symbol beta 0 represents the baseline yield, meaning what the outcome would be if absolutely zero treatment was applied. The symbol beta 1 represents the treatment effect, specifically the increase in the outcome for every single additional unit of x sub f. As x sub f increases, y sub y will increase at a rate determined by beta 1, while epsilon still accounts for uncontrollable random factors. Let us apply this linear regression formula to a practical agricultural example. A researcher wants to determine the optimal amount of a new nitrogen-based fertilizer to maximize wheat yield. The field is divided into equal plots, and different amounts of fertilizer are applied. We use our regression model, where y sub y is the total wheat harvested and x sub f is the fertilizer applied. After analyzing the data, the researcher finds that beta 0 equals 2,000 and beta 1 equals 15. This means the baseline yield is 2,000 kilograms per hectare. Physically, this tells the farmers that for every single additional kilogram of fertilizer applied, their wheat yield increases by exactly 15 kilograms. Now that we have successfully used these mathematical models, let us zoom out and look at the overall structure of how these experiments are actually conducted. Every rigorous experiment follows a strict logical sequence to ensure validity. It always begins with a clearly defined population. From there, subjects are randomly assigned to different groups. This random assignment is crucial because it evenly distributes any hidden extraneous variables, eliminating inherent biases. One group receives the treatment, while the other serves as a baseline. Finally, the outcomes are carefully measured and compared. This structured approach is what makes the math we just learned actually work in the real world. To visualize this structure we just discussed, let us look at this flow chart of experimental design. At the very top, we start with our target population. Following the arrow down, we reach random assignment, which is the critical splitting point. From here, the path branches into two distinct groups. On the left, we have the experimental group in blue, which receives the specific treatment X. On the right, we have the control group in orange, which receives no treatment and acts as our baseline. Finally, arrows from both groups converge at the bottom, where we measure and compare outcomes, which is our dependent variable y. This diagram perfectly summarizes the journey from a broad population to a definitive cause and effect conclusion. As we wrap up this lecture, let us reinforce the most important ideas we have covered today. First, experimentation is the ultimate tool for establishing definitive cause and effect relationships by actively manipulating an independent variable. Second, we learned that strict control of all extraneous variables is absolutely essential to isolate the true impact of an intervention. Third, we saw how mathematical models, from basic equations to linear regression, allow us to quantify these relationships precisely. You have now covered the fundamental principles of experimental design. Mastering these concepts is essential for anyone looking to contribute rigorous, reliable, and actionable knowledge to the scientific community.